Let's look at another example, that of waves travelling on the surface of water. We are once again interested in the phase speed, Cp, and we happen to know that these waves depend on fluid depth, h, gravity, g, and wave number, k. In this case, I'll write the problem slightly differently, to include the left-hand side in the non-dimensionalisation from the very beginning. In other words, we write Cp equals an unspecified function of h, g, and k. The units of Cp are in metres per second. The units of h is in metres, g is metres per second squared, and k is in inverse metres. So on the right-hand side, we have n equals 3 variables and m equals 2 independent quantities, meaning that we expect just one dimensionless group here. This dimensionless group can be found by multiplying through by h, to give Cp it being a function of gh and kh, with units of metres squared per second squared and nothing, respectively. So we found our dimensionless parameter. It's just kh. But why did we need gravity at all? Well, we needed it to non-dimensionalise the left-hand side, which we're going to do by dividing through by the square root of gh to give Cp on square root of gh equals an unspecified function f of kh. Again, this compares well with the known solution, which you'll derive yourselves in week 9 of this course, and that is Cp equals square root of g on k tanh kh. Okay, let's do one more worked example here using something that you know and love, a simple pendulum. Let's assume that the period t of a pendulum depends on mass, m, gravity, g, and the length, l, of the pendulum. Then we write our problem as before. T equals a function of m, g, and l, with units of s, seconds, kilograms, metres per second squared, and metres, respectively. In this case, we find that we have n equals 3 physical variables and m equals 3 independent quantities. In other words, we need 0 dimensionless parameters to describe this problem. This is actually telling us that the mass of a pendulum doesn't modify the period, and the right-hand side is constant, meaning that all we can do is to non-dimensionalise the left-hand side and set it to equal a constant. In this case, we have no choice of parameters. We have to write t on the square root of L on g. This is a pretty special case because dimensional analysis almost gives us the correct answer. So, I hope you found that illuminating. Just to summarise quickly, today I've introduced to you the Buckingham Pi theorem, which says if the behaviour of a system is governed by n physical variables which depend upon m fundamental independent quantities, the system evolution may be described by n minus n dimensionless parameter groups. To apply this theorem, what you need to do is decide on the n physical variables of the system, noting that your answer is actually sensitive to this choice. You need to count the m fundamental independent quantities, and this will tell you how many dimensionless parameters you need to describe the system by subtracting m from n. To find these parameters, systematically eliminate units from the list of physical variables. Then, write your dimensionless variable as a function of the n minus m dimensionless parameters. Remember that the answer is not unique, and that combinations and powers of your parameters are also valid answers. Obviously, dimensional analysis needs careful application, but it is also a powerful tool that can give you understanding with a relatively simple application.